Good evening, everybody, and welcome to the Heliophysics Community Practice Monthly Meeting. Tonight we have an exciting agenda where we are going to hear about a spectroscope that can be used in the classroom. Lynn Powers is going to show us how to build one, and also Claire is going to do a presentation about some unique spectra data. So we have an exciting presentation, and I'm going to turn it over to Lynn now so she can get started.
Hey, thanks. I know that they had talked about doing one with fraction grading, but I sent in an email with one that I had done using a cereal box with a CD, and it's a lot easier and it's found items. And so I'm going to show you how to do that. I have posted in the Widgio as well as in the chat box the website that I am going to be doing. So if you want to have two windows open, is anybody going to help do it with me? Or should I just run through it really quick? So supplies you're going to need a box. It could be a cereal box, any type of box. If you're like me, you probably went shopping right before. So make sure you take the contents out. You're going to need an empty box. You are also going to need a CD. You are going to need a pair of scissors. You're going to need the aluminum foil. You're going to need some tape. You're going to need a template or a protractor to help you get to 60 degrees. The template is part of the online. If you followed the post, there's a place where you can click for a template, so you don't need a protractor. A writing utensil so that you could be marking it. And if you're like me, you need to have safety goggles or reading glasses so that you can read the directions. Also, what I posted on Widgio, there was another one that I found, and you can buy a cute little thing like this to put on your cell phone, or there's a template on there where you can print it. I printed it and put it on some construction paper to block out the light. I put it together. You put diffraction grading in there, and I'm going to show you what it can do. I'm going to put it over my camera. And can you guys see a little bit? Where'd it go? There it is. Can you see that? So this was something that I printed off the internet. Unfortunately, I used glasses, and as you can see, the diffraction grading in there is not the really good diffraction grading. So I'm thinking that's part of the problem that I'm having with that one. But with this one that we're going to do with the cereal boxes, you don't need diffraction grading. You can use old scratch DVDs. So what you need to do is, if you go to the website, all the directions are there. And what you're going to do, first of all, is you're going to take some rulers and you're going to measure in. It says 1.5 inches. You're going to mark it. Then you're going to grab your handy dandy trusty scissors. And you're going to open that up. And that's the hole that we're going to be looking into after we put the CD in there. Also on the Widgio, I posted some other links. One of them was how to find this. There was also one where you could make one of these with a huge packing box, and you can put a lot of kids' heads inside there. I haven't tried it, but if it's on the internet, it's got to be good, right? We'll see.
Lynn, what did you just hold up to show? That, not the box, the other thing that you posted where you can find what? I missed that.
These things, this
Oh,
this
okay.
make yourself one.
Okay, thanks.
So the links for this, as well as the big box spectrometer, they're on the Widgeo. Does that make sense?
Yep.
Okay. I should have like 5 of these with different sections so that I could be doing it real quick, where half of this is done and the other half is done, like on TV. Sorry. So who's doing it? Nancy, you're doing it with me? How you doing? Who else is doing it with me? Woohoo! Molly. Okay. So next we cut that off. We need to use our triangle to draw the guidelines across the width of the box, because we need to be able to put our 60-degree angle in there. So we're going to be measuring down the 6 inches. And if you have one of these and you know how to use them, you know how to put in the 60-degree angle. So what we're going to be doing is that on both sides, going down 3 inches. Does that make sense? Do you guys have the link open too? So I'm going down 3 inches and drawing a line. I'm measuring down 3 inches, and then I'm measuring 3 inches and I'm drawing a line on both sides of the box. And then I'm going to be putting my 60-degree angle in there. Okay? I guess I should have brought an extra camera home too, so you guys could see what I'm doing. So I'm going to get that on both sides. And that's going to be the holder for my CD. Does that make sense? Now on the opposite side, over here, I'm going to measure down 1/2 inch and draw my line. And I'm going to measure down 1.5 inches and draw another line. So I've got down 1 inch to 1.5 inches. I've got 1 inch right here. I need to take that out. And if I stick a hole in it with my pen, I'm going to cut that out. And no, it doesn't look pretty. And it doesn't have to look pretty because we're going to be covering this area with foil. So you're just cleaning it out. Doesn't have to be pretty. You guys got that? Now you're going to cut some foil up. And you're going to bend it in half. one for the top. One for the bottom. So that hole that we just cut on the opposite side of where our CD is going to go, we are going to put these, tape them on, and we're going to leave a slit that's 1/2 to 1 centimeter. This is where the light's going to come through. That's going to bounce off our CD that has those raised ridges. That's going to give us our spectrometer readings. So we're going to tape these onto here.
Hey, Lynn, did you mean 1/2 to 1 millimeter?
Yes. Did I say centimeter?
I think you might have, but
that's way too big.
What would happen if it was bigger?
I would think that if it was bigger, I would be able to see the light bulb. I'd still get some spectra, but I'd also have I would also get the image of the candle or the light.
The spectrum would be mirrored also.
Would it be mirrored too?
Mirrored. In other words, instead of having distinct lines, it'd just be like a rainbow.
Ooh. Makes me want to do one wrong just to test it out.
That would be a good inquiry question so that kids could try different widths and to describe what happens as it gets narrower and wider.
So how are we doing?
That's a great idea, Sally. How else do you guys imagine that you would be able to use this?
Do you guys see my slit in there?
Yeah.
Hi, Don. This is Molly. Just to answer your question, when I cover light and optics with my students, go over the electromagnetic spectrum and then the colors, Roy G. Biv, the 3rd through 5th grade. So that would be a great activity for them. I actually have one that's a fraction grading pair of glasses, and that's what they use, and they just look up at the light and they're all amazed about it. But this is something they can actually make.
That's awesome, Molly.
Make sure you tape the top of your box closed. You can put this back in, and now you're going to point a light source to your slit, and you should be able to get some spectra. Can you see anything?
Blue to green really well.
Can you see it?
Now, the colors on the actual CD, that's what we're looking at?
What's that light you're shining on it?
I think if you tilt it down a little bit, Lynn, we can almost see it, but it's just out of the camera.
I'm trying to.
Down a bit more. Tilt the end of it down. There you go. Now try again. That's hard to see on the camera.
Okay, y'all may not be able to see it on the camera, but this is way cool.
So I've got some different light sources here. What do you think?
I like this. This is neat. I like this. Because like you said, I mean, this is something that the kids can make. I mean, we have, like as Molly was talking about, we have diffraction grading glasses, and we have spectrometers that we can use at school. You know, the plastic ones from Flynn Scientific and all. But what's really neat about this is that, as you were saying, the kids can actually make this. They can take it home. That way, I won't be missing any equipment from my lab. So I'm liking this. I'm liking this a lot. Very cool.
I'm going to share my screen real quick. This is a website that I shared on the Wigio that has some spectra already, and you can join. There's a whole bunch of stuff on here, so the kids could try to figure out what their spectra is doing, what they're seeing. And look, there's a whole bunch of pages.
Wow. Okay, that's cool.
So questions? Well, most of these things, luckily, they can be done with stuff that most kids will have at home.
Yeah.
And I cut my holes too big. It's not holding my my CD.
Oh.
Has anybody ever done an activity like this in their class before?
Not with building one, but using the smaller plastic spectroscopes that we have at school. We've used those quite a few different times. So I like this.
Now, have any of you guys made these?
Here's a plug.
Yeah.
Arbor Scientific. What makes these nice, they show you the spectrum on this side, then you flip the card over and it tells you what the light source is. So they actually have something to compare, and the diffraction gradient is right here in the small hole. You're impossible not to be able to use them.
Very nice.
It's a card that's very inexpensive from Arbor Scientific.
Arbor Scientific.
Yeah, but the catch is you miss the ability to build them, and I think that's might be more important in this case, the building of the model versus using it.
What you could do is have everybody build them and then have a few of the high quality ones to use as kind of demo in the classroom or something like that, so you get the best of both worlds.
If you guys still have the overhead projector film, you can print out some spectra too. You don't have overhead projectors anymore, Vic? Huh? Did you get rid of them? Okay. So I think I'm done. I did post some more pictures or some more things on the Wigio. Like I said, I found this big, huge box. So with it being the International Year of Light, I was thinking that would be a good thing to do with one of the summer camps that I'm doing with the kids. You get a lot more heads inside one of those boxes than you can inside the cereal box.
This is really cool, Lynn. Thank you so much. It was awesome.
You're welcome.
Do you guys have anything to add about how you would use it, or any suggestions for the people that that'll be watching the video about how you could use it or have used it in your classroom, since you all teach different age groups? Thought it might
Have
be.
them go for a walk outside at night, and you get the sodium vapor lights, you get the mercury vapor lights. You go into the gymnasium. Most gymnasiums will have the yellow sodium vapor and the very blue mercury vapor lights. You get completely different spectrums. Look at an incandescent light. It gives them something to do at night instead of getting into trouble. But you can use this device and begin to identify what kind of light sources, not so much what they are, but they're different. And it's how your eyes see red, green, and blue. It's how you get the colors you get. And so it's kind of a nice exploratory for, hey, kids, go out, get dad, go with you, and go for a walk, look at the street lights, kinds of things.
Yeah, and this is also a good way, when we do certain, we start looking at chemistry, and we start looking at periodic table and different elements. We do a flame test, and I'm sure you guys do that because it's very, very simplistic, but this is a good way of, well, using spectroscope, or using the spectrum is a really good way of introducing what it is we're going to be seeing element-wise. And before we get to the flame test, we always do bring out, our small little, our little guys so that the kids can see it. But like you said, when they have the box like this and they can take it home, they've made it with us, take it home, then they can experience a whole lot that we can't show them at school. Like you're saying, the mercury vapor lights. We don't have the kids here when it's dark. I like to get rid of them before then, but they can certainly experience that, so that when we actually are doing our flame test and they can see what's coming up, then they have a better experience of what's actually happening around them. So I really like that.
So this is a non-teaching experience question, but how much detail do you go into, or do you have the opportunity to go into, about what the actual spectrum is, or how it can be used as a tool in real science purposes, and like outside the classroom, how scientists use this as a tool?
Well, for us here in Texas in middle school, 6th grade through 8th grade, because I have both groups this year, we do an awful lot of how you can use the science, the real world application of things. In 8th grade, it's very important that we bring in careers in science. So the kids, each unit that I do, there's always a certain set of scientists that my students have to go out into research into. What are they doing with this? What are they doing with that? So with using, using the spectrum like this, of course, here in Texas, skin cancer, UV radiation, all that is a really big deal, but they branch off into all kinds of other things as well. And I've been getting some very interesting reports, just of what they can do with it. So you usually start it out with, if I were a scientist, if I could get a job, and this gets them thinking about what path they want to take when they get up into high school. So that's what we do with it.
I use it in my chemistry class. Basically, just when we get into quantum mechanics, Planck's constant, different frequencies produced by excited electrons, and not so much detail as I use gas tubes, simply because it gives you much clearer spectrums. And what we do is we discuss, and I've got, over the time, I've got a half a dozen of these different elements. So they can begin to compare elements. And then we go into the helium story, which was discovered on the sun. And then we explain, well, how in the world do we know what elements do we find in some sun that's 1,000 light years away? And for high school kids, it takes them about that long to figure out, oh, you use a spectrum. So it is, that's where I can bring it into my chemistry class and still be teaching some space science in a chemistry class.
Good.
Yeah, at the planetarium, we used to do a demo. That was basically, we found this new star and its spectrum looks like this. See if you can add the spectra together to, figure out what it's made out of.
Yeah.
You have to sort of think about the absorption versus emission, but it was fun to do.
There's a neat, I think it's on the Chandra website, of the picture of the Crab Nebula in different wavelengths, so that students can see that an object in space looks different. I think, I'll post it if you aren't familiar with it. I'll just have to look for it. But it shows how things can really look differently, and that's how they study astronomy and how they study the stars is because of the different footprints or the light print that different elements have.
I use this in astronomy. Go into the spectra and then do the same thing with the different gas tubes. And then they have to identify what element it is. And then I go into talking about, I use hydrogen as an example on how the red line on hydrogen, if it shifted to the red shift or the blue shift, and then we talk about the Doppler effect, and we go into the expansion of the universe, and we calculate the radial velocity using that shift in the line, how many, or the wavelength shift. I don't know, they get into it.
Are you talking about Doppler shifts, Wendy?
Yeah, the Doppler shift, because they understand it with sound. They've heard that, and they've had it explained to them with sound, but I'm the first one that talks to them about it with light. And they get it because of sound, and then I transfer it to light. And then they can see how we can tell the universe is expanding because of that.
I remember when I was starting my PhD, that was one of the main tools that I used to do my analysis. And I was looking at whether or not solar flare foot points were exploding, basically. So you get all this energy dumped into a little region, and then if you look at the Doppler shifts, you can tell that it basically explodes up into the loop, and you can see the blue shifts towards you and the red shifts going down towards the sun, and you're able to characterize it. And from that, then we're able to take a leap and look at the density of those two to see the difference between them.
Very cool.
It's interesting.
That's neat.
Yeah, I remember my physics professor when I was in college standing in the park just outside the physics building with an LED on a string, and he would swing it around his head to try and do the Doppler effect. I can't remember what the results of that were, but it's worth a shot.
Yeah, that's
I was about to ask you, did that work?
I must have, because he did it every year, so I just can't remember what the results were. I think there's a YouTube video online. I might look at it.
I kept breaking the wire. I wasn't spinning it at the right way.
Let me see if I can find. Oh, here we go. Dancing Doppler.
Yeah.
Oh, it was a sound effect. It wasn't.
Okay.
The source coming straight at you and straight wavelength. But also, what happens if you cross your field of view? Is there a Doppler shift? It's going to run around in circles. And I can demonstrate that by doing the wind fill. And what I'm going to do is this. And when I'm facing you, you shouldn't hear any Doppler shift, or hardly any. But if the people try to go, they'll hear the Doppler shift. So you'll only hear the Doppler shift when it's coming towards away from you. And this is the window, and I'm going to turn around so you're all going to hear it. Okay? Now you shouldn't hear anything, you should. Now turn around. Okay? You shouldn't. You should.
Anyway, sorry. I thought he did it with LEDs, but it's actually just a little buzzer. It's still fun. It was always a fun experiment to do. Because he wasn't the youngest of professors, so I was always afraid that he might break his arm or throw a hip out or something when he was at it.
That was cool, though, on how he was turning. So if they were right in front of the thing, they wouldn't notice anything. If they were on the sides, then they would notice the Doppler shift, right?
Yes.
Cool.
I just put the link in the chat window if anybody wants to watch it again, maybe with better
Very cool.
Chris, you mentioned that you have you go fairly deep into the uses of spectroscopy. Do you want to fill us in?
You guys hear me all right?
Mm-hmm.
Okay. We've been doing a lot with making our own spectroscopes. When we, one of the gals in the Maven Educator Ambassadors program showed us a DVD spectroscope you could build using the DVD case and the DVD and some things on the side of the screen and everything. And you can look at the sun's absorption lines with that. I never had a way to have kids look at absorption spectrum before that point. We just would look at emission and continuous. So that was a good way to get that introduced. And again, like Vic said, talk about how, you know, they discovered helium in the sun before they found it here. We were involved with a Mars imaging program once upon a time, and some of the stuff online included use of a reflectance spectrometer to get the reflection spectrum of different rocks and things, and then compare that to known minerals and identify what minerals were in the rock and that type of stuff. So a little bit more than I used to do in astronomy before that point.
Very cool. Hello, Andy.
How was your flight, Andy?
It was good. It was good. Hi, everybody.
Diane, you were saying that you do a lot of really interesting things with spectroscopy as well. You want to fill us in on that a little bit?
Well, I just can't leave them alone. And so all my classes wind up looking through diffraction gratings at, you know, any light source we've got. I have them, they're taking pictures of things when we stand eggs on their ends for the equinox myth. They're taking pictures of that through their, you know, diffraction grating, all kind, you know, LED lights, whatever. So they have a lot of fun with that and explore it. And then of course, yeah, we've got so that's kind of normal, but what they'll do is I encourage them, go ahead, whip out your phone and see what you can do with this. And if you get something good, send it to me. So they send me great pictures all the time. And so I post them and they can kind of evaluate each other's work, and it's fun.
Very cool. I like how you were saying that you use it across all the disciplines, from biology to...
Well, the first time I ever did it, was 35 years ago. I was a biology teacher, and I discovered that thing about if you take the chlorophyll molecule out of the chloroplast, you get this magnesium, you get this wonderful red glow. And so, I mean, Spectra had me from that moment on. Because that emission line just got me right there.
Claire, did you want to tell us about your research?
Sure. So this is a little, I won't say it's a pet project because it does actually pay my salary, but it's kind of a different type of project that I've been doing for the last few years. I was going to just share it with you today just because I can. So here we go. So it's entitled "One Woman's Trash is Another Woman's Treasure" for good reason, and hopefully that will become clear as we go along. But in the meantime, you can just trust me that that's where we're headed with this.
Claire, there's a request for you to speak up a little bit.
Oh, I'm sorry. Let me see if I can move a bit closer to my screen. Maybe does that help?
Or else turn your mic up, Claire. It's almost like you're whispering.
Okay, let me do that real quick before I go on. Automatically adjust microphone settings. Is that any better? No.
I can hear you okay, so it might just be that Andy's background is loud.
Okay.
I can hear you.
Is that okay? I'll try and talk a little bit louder.
You're louder now.
Okay.
No, it's much better now. It was just Claire I couldn't hear. I could hear everybody else fine.
I was going to start singing a song, but I won't. So. Okay, so the Solar Dynamics Observatory's atmospheric imaging assembly telescopes. There's 8 of them, and there's 8 EUV telescopes. And we've heard a lot about them over the last 2 years, so I'm not going to go into detail about the telescopes. You guys know what these are, and if we have new people who are watching the videos, then there are a whole host of different resources that we've gone into over the last few years that you are welcome to go and pursue. However, I do want to take it in a slightly different direction today. So this is a pretty typical picture. Actually, this is today's picture of the sun. This is just a few hours ago in a particular passband. So it's called the 171 angstrom passband, which doesn't mean much other than the fact that it shows us emission from the sun at about 1 million degrees. Okay, but what we're going to figure out today is that it's not at exactly 1 million degrees. So the way the telescope works is that there is light emitted from the sun at all wavelengths, and it leaves the sun and it travels towards the Earth, or really towards our spacecraft is what we're interested in, and it covers the whole spectrum. So not just the EUV that we're interested here, it goes all the way from X-rays through to radio waves and everything in between, and every now and then even goes as far as gamma rays. The light hits the telescope and it passes through its front apertures that I don't seem to have access to a mouse here, but it's basically what you can see inside that little square box with the 4 colors. They're the 4 telescopes, and each telescope has 2 filters on it. So each telescope sees 2 different wavelengths of light alternating. So it will look at one and then it'll switch to the other and then back to the first and then back to the second. And that's why we can see 8 different EUV filters, but only using 4 telescopes. And inside those telescopes, there's a whole series of specialized optics. So there's special coatings on the mirrors, and there's some filters, like very thin films that they put in there as well, that preferentially transmit only a small region of the spectrum. And so it looks something a bit like this. So this is just a small region of the extreme ultraviolet spectrum around the 20 nanometer range, and only for the 171 passband that we're looking at here, only emission from about 15 to about 22 nanometers. So 10 angstroms is 1 nanometer. So 15 nanometers is 150 angstroms. So for some reason, astronomers work in angstroms and the whole rest of the universe works in nanometers. I don't know. It just goes to show how arcane our field is. Anyway, so through our telescope, only a very small amount, a small region of wavelength is allowed to pass through. And then that gets to the detectors, to the real camera piece at the back of the telescope. And basically all of those emission lines that we can see here, they all just get added together. The total number of photons in that little region of wavelength all get added together, and it spits us out a single number, and that's called our data number. And it's basically 1 number per pixel. So if you go back and look at the image in the top left corner, basically all that is just a whole array of single numbers, but each one of those numbers were created through this process, basically by summing up all of the photons that make it through the telescope per pixel on a given pixel. So that might be a lot of information. So if anybody has questions, I'm happy to take questions just now before I move on, because if I lose you at this point, then we could be in trouble later on. So is that clear how we go from it being all light emitted by the sun to just getting a series of individual numbers that create a picture? Okay, I'm going to take your silence as a yes and carry on. Okay, so I mentioned earlier that inside our telescope, so inside, can you see my mouse? Yeah, okay. So inside, I'm going to do this so as I can use the mouse. This is helpful. Inside our telescope over here, each one of these 4 telescopes has very specialized thin films and filters in them. And they're not the same for every telescope. They use different coatings and different films depending on which band of emission they want to see. And they look a little bit like this. So this is a very poorly rendered graphic of the inside of an AIA telescope. So the entrance filter here, the light comes in through this red circle on this end, and then we have the wavelength selector. So I said that it flicks from one wavelength to the other. So this is basically just like a shutter that swings from one side over to the other, depending on which wavelength we want to look at. Then it passes through the secondary mirror and through to the primary mirror here. And so this has a special coating on it, and it's reflected back to the secondary mirror, and that has yet another coating on it. And then it goes back here to the shutters and then to the filter wheel assembly. So this is the shutter assembly. This is basically like pressing the button on your camera. And then you go back to the filter wheel assembly, which is where these thin films are. And there's actually 2 films per wavelength. And then you finally make it through to your detector. So through this whole series of bouncing back and forth, basically eliminate all of the light that you don't want to make it onto your detector, and only the light that you really want to see makes it as far as your CCDs. And what I want to draw your attention to just now is this filter wheel assembly. So the filters look a little bit like this. So this is kind of a zoomed in version of it. And you can see that they're basically a whole series of very thin lines, and they're actually like etched into the filter. I'm sorry, that's not what I meant to say. The reason that these are here is that the films are so thin that they have to mount them on something. If you just like hung them around the edge of the filter, they wouldn't be able to support their own weight. So they basically attach the film to this grid, this hexagonal grid that looks like this, in order to keep it upright. So this is all important down the line. Trust me, I know it may not make sense just now, but this is really important. And every one of the filters has one of these grids with a slightly different crosshatch, but they all have 2 sets of grids that are sort of orthogonal to each other. And it's a little bit like, you know, those glass windows where you put the wire mesh through them. So if you break the window, it doesn't shatter. It's kind of akin to that, but on a much finer scale. Okay, so
Claire, I have a question. What is the purpose of the cross hatching? Is it the same thing, like for protection, or is it?
Yeah, so the crosshatch is just a support mechanism. It's just
Okay.
the thin film. It's basically just like a skeleton to put the film on, because the film is so thin that it can't support its own weight. So you just basically put the film over this crosshatched mesh skeleton essentially, and the skeleton just keeps it in place. But we actually want to use this crosshatch where most people, it's a hindrance to most people's analysis. So it's really just an incidental byproduct of how the telescope is made. It's not deliberate.
Thank you.
Sure. Any other questions? The pretty movie play. Well,
I have a question, Claire. It's about the engineering part of the instrument piece. So are those yeah? Oh, don't you need to stop the pretty movie? I'm sorry. But when you said it goes through the secondary mirror, it's going through. It's being aimed through those different pieces, right? Because that was, and so it goes through, but then reflects back onto the surfaces that are coated on the other side. Is that correct?
Yes. So that's pretty typical practice in telescopes, where the light passes through a hole in one mirror, and then is focused on the other mirror, and then gets reflected back onto the actual mirrored piece of this.
Okay, cool. I was just reading the diagram going, wait a minute, won't it just reflect? Because I wasn't listening, I was reading.
But it's the way it comes through. And this diagram doesn't have enough detail on it for that really to be clear, but that's almost positive that's how that works. But yeah, that's certainly how I would read it from this diagram anyway. Okay, so I'm going to let this play for a second, and I would like you all to tell me what you see. It's like being in school. Don't make me start picking on people.
I see a CME, and it looks like there's a flare going on too.
Very good. What else do we see?
It looks like there's a reconnect down there someplace too.
Down here?
Yeah.
Yeah, quite possibly. So I want you to think beyond the phenomenological observation. I want you to really look at just What smacks you in the face?
Okay,
Oh,
we're
yeah.
getting a diffraction grating effect.
Yes,
Right.
we are. We're getting diffraction.
Oh.
Okay, what else do you see? What's going on up here and down here?
Well, it looks like, you know, it's like lightning-ish.
Yeah, so this is called blooming or saturation.
I was going to say, is that from the detector getting saturated almost?
Yeah, so when you get a solar flare, there's just so many photons that the CCD cameras can't cope. So it's a bit like taking a photograph directly at the sun using your cell phone camera, and all you're going to see is white. You're not going to see any detail. You're not going to be able to see anything of value, and it's kind of akin to that. Basically, what happens is your pixels get so saturated that the extra photons that try to get into each one of those pixels, they spill along other CCDs into other pixels, and that's why we end up with this blooming effect. But when you're trying to do scientific analysis, you see this and you're like, oh, pretty CME, oh, something going on in here. I can't really tell what it is because it's just white. This is not helpful. This is not really useful for doing any kind of analysis. Basically, it's just like chopping off the top of any kind of light curve, or you can't tell what's going on here. You can't get any kind of detail out of this. So that's not really very helpful to us as scientists. And most scientists will see something like this, and they will use the upper half of this image, or they will use other complementary data sets, but they'll pretty much just throw this piece out because they just can't use it. There's no way you can use it. But this is where one man's trash becomes my treasure, and I've basically built a research project off of this this phenomenon, and I love it because it's very, very straightforward. So this is my little cartoony diagram of what's going on. So this is our telescope, and we have the light coming through the telescope and going through this filter mesh that we talked about earlier on, and this is just a blow-up diagram of what we see. So this basically ends up behaving a little bit like a diffraction grating. So the same way as a diffraction grating has lines etched into it, instead of the lines being etched into it, these are the lines are almost superimposed on the filter, but it has the very same effect as a diffraction grating. And what happens is the light that gets spit out the other side, if it's bright enough, ends up having this this beating pattern, this interference pattern effect, basically. So you have this place out, this middle order, we call each one of these as an order. This middle one here is the central order, and this is kind of the truest of all of them. So actually what you would see if this was real data is this would be chopped off right here. This would be plateaued, where it will have saturated, and all the excess spills out into these other parts of the diffraction pattern. But the point is that we can see this, and if we go back to this image, you can definitely see the diffraction patterns up here, and you can see how they overlap. So each bright pixel produces a diffraction pattern, and there's 8 arms, 8 of these for each bright region, because we have these 2 overlapping quadrants. So you can see that it's a whole big hodgepodge of mess, but that you can definitely see the diffraction patterns happening up there. And then the even cooler thing, at least in this is spectroscopy nerd-tastic right here. If you go to high enough orders, so if you go far enough away from the central wavelength, you just start to see dispersion occurring. So not only do you see this beating pattern for diffraction, and this is helpful because you're able to basically fit a very simple physics equation that will tell you what this true value needs to be in order to fit the rest of these patterns. So that means that we can figure out what this central wavelength, or what the central intensity actually is. So it can tell us really how bright the pixels are, as opposed to what the cutoff value is that the camera subjects us to. But then we can take it a step further and go high out away from the central region, and we can actually start to pull apart the individual diffraction orders to try and get back to that original spectrum that we saw back here. So basically, where we took all of these lines, all of these pieces of the spectrum, and just added them all together to give us one number, we're basically now taking that one number and we're piecing it apart to try and get back to the distribution of these emission lines at different wavelengths. So it's kind of wacky and a little bit crazy, but it's spectroscopy. And this is really valuable for us because there's a whole pile of science that you can't do, especially around solar flares, unless you have high cadence and high spatial resolution. So you need to have really finely distributed pixels, and you have to be taking pictures on a really fast basis, basically. And most of the other instruments that can do this for us, they just by the way they're built, they have to be slow. So the other next best instrument that we can do this with either only looks at a teeny tiny region of the sun, smaller than that movie that I played for you, or it takes one picture every 5 minutes, which is no good if you're talking about something that changes on the scale of tens of seconds. So the hope is that we can try and use this to try and do better science with it as a result. So this is one of the examples that we put together recently. So this right here, this is a highly processed image of the sun. So right in here in the middle of this is our solar flare, and you can see that it's saturated, and we have this blooming region right here. And because of the way I've processed it, you can see that we can see these diffraction orders, the diffraction arms, all the way out to the edge of the camera. So this right here is the edge of the sun, and over here, this is the edge of the camera's field of view. So you can see that we can see the diffraction orders all the way out to here, and this is about 50 orders away. And then this is basically like a slice through this diffraction arm right here to try and see if we can see that beating pattern. So you can see it fairly well. See that it's not as nice and smooth as the cartoon version, because real data is never nice or smooth. But you can see that you start to make out this kind of beating pattern. And we can pull apart each of these, and we can start to work out, based on what we know about the passband and the telescope itself and the engineering that went into developing the filters, we can work out what the actual spectral components should be, or are, I should say, not should be, once we get out to far enough orders. And to prove this to you, here's some examples. So these are two spectra from the same pixel but at different wavelengths. So these are basically two different telescopes, and we've taken that single data number that we had at the beginning and we've pulled it back out to try and look at the spectral distribution of these. So this black line is basically that's what the deconvolved is the word that we use, the deconvolved pixel distribution for the 193 passband, which is quite hot. And then over here, this is the one for the 211 passband. So you can see basically these peaks and troughs, these are all emission lines. And actually, I cropped this image, but maybe I shouldn't have. So if I do this, I think, there we go. This is this colored hodgepodge up here. These are all the spectral lines that we see in this passband, and they change quite drastically with temperature. So this is the log of temperature. So this is 1,000,000 degrees, 10 to the power 5 is 100,000 degrees, 10 to the power 7 is 10 million degrees. So this is going up in powers of 10, basically. So around 500,000, we have a bright oxygen line right here. If we go up to a little over 1,000,000 degrees, we have these three blobs at different wavelengths, but they're all around the same temperature. So this along here at the bottom, this is wavelength. Oh, I managed to cut the wavelength axis off, but you can trust me on that one. And then as we go into even higher temperatures, we have these really hot components. So this is an iron atom with 24 electrons stripped off it. So that's pretty darn hot in order to be able to successfully do that. And what we were able to do is basically add different components of this together to try and figure out what the temperature is of this contribution to the spectrum, which is something that you can't do with AIA or really with any other kind of data. So it's a bit wacky, it's a little bit out there, but I just wanted to sort of give you an idea of what it's like to do real spectroscopy. It's sometimes very, very tedious, and it can be very frustrating, but when it works, it is extremely rewarding, and it can tell you more about any of the parameters than in any other way. So it's always well worth it. So that was a lot of information in a short period of time. So if anybody has questions, I'm happy to answer them.
I think I got bounced around, so I missed part of this.
Okay.
And I followed you up to the pattern where from the pattern, you can determine the wavelength of that light or whatever you're looking at, correct? How did you convert that into your temperature?
So I'm confused as to which pattern you're talking about.
When you look at your pattern of your spectrum, the distance between the lines right here. This pattern from your center bright line to your center bright line to your center bright line, that is basically can be used to determine the wavelength of this specific light. Is that what you were saying?
Yes, let me show you a different picture. I have it. Oh, I have it right here. How helpful. So I left this out because I thought it might be too much detail, but I will show.
I'm sorry, but I think I got hung up about 4 or 5 times.
Oh dear. Okay. All right. This picture here. All right. Let me walk through this line by line. So this is a funny looking slice through the image. It's basically the very same as that green picture with the arrows pointing up to the far right corner, and all I've done is rotated it so as we can take a slice through it. Okay, so that's what this green picture is. This blue picture on the end is just this little region. It's the very same thing, it's just this region highlighted. All right, so then if we take a slice through this picture right here and just look at how intense each of the pixels are as a function of distance away from our solar flare site down here, this pattern is what we end up with. So this is our beating pattern or interference pattern that we talked about earlier on. All right, you with me so far? Vic?
We can see you, Vic. We just can't hear you.
I muted my mic, so I'm going like this, so you don't get any background noise.
I had the picture minimized. I'll leave it up just for now. Okay, so you're with me so far. Okay, so now if we take a small region of this this pattern right here, so this blue hatch line down here, and we plot this out again. So this is still just basically just blowing up this section, and this is what it looks like. So you can start to see that there's a repeating pattern in this. So we've got this big peak, this big peak. It's not exactly the same, but it's fairly comparable, and then 2 smaller peaks, 1, 2, 1, 2 smaller peaks. And then if we take this one here in the middle, this this region right here corresponds to the same region that we saw during that first sort of circular diagram where we went around the world. Let me see, can I share a new window? I'm just going to do this, and I can share them all. So this little red region, now it's not exactly the same picture because this is a different passband and a different event, but all these individual little peaks correspond directly to this section right here. Now, there's a very simple equation that goes with this. Let me see if I can find it in here. Here we go. So this is basically the equation that you use, where theta is the distance from your flare, lambda is the wavelength that you're using, and in this case we don't use a single wavelength. We go from, instead of it being just 17 nanometers, we go from 15.5 nanometers to 19 nanometers, and we work out this equation for each one of these, and then we can tell what the distance away from the solar flare site should be, provided we know these 2 numbers. So m is the order number, so the order is basically each one of these peaks is an order. So that's actually difficult to identify exactly just because it's all kind of blurry in the middle, but you can work that out. It's just counting. And A is the size of our grating. So it's just the distance between our 2 grating numbers. And
okay, we do this in class with a laser beam and gradient, and you know the distance to the screen, and so you can actually calculate the frequency of the wave that comes out of that laser.
It's the very same thing. That's why I love this.
Okay, that's the same thing. So I'm following you so far.
Yeah, it's basically high school physics. This is not difficult. It's tedious, and it's because it's applied to a research project. It's surprisingly kind of unusual to see anything like this. I think we're the only people doing this kind of work on this particular spacecraft, but it's very straightforward physics. It's really simple. So once we get to here, this is now a spectrum. So we've done that conversion, the theta to lambda conversion, where these arc seconds are theta and lambda is down here now in angstroms. And once we do this, then we can fit it. So these models here, these are generated using atomic physics computer programs basically, and they tell us what we should expect the corona to look like under certain conditions. And so we compare a whole bunch of different conditions, and then we just work out which are the most likely or which are the best fitting conditions to our spectrum. So this up here was the 193 spectrum down here, so that corresponds to this guy right here. And so you can start to identify what the different temperature components are, but it's really very straightforward. That's why I wanted to share it with you, because it's something that, you know, you like you said, you do in your classroom, but we're applying that very same principle to do revolutionary cutting edge research science. Who knew? So does that clear things up?
That made it a lot clearer for me. Thank you.
Does anybody else have any questions on either this or spectroscopy in general or anything?
So since we have all of the archive data, are you going back and looking at old events and coming up with this, or are you just starting off with the new events?
No, we're looking at old events. So we're trying to develop a mechanism where we can do this in an automated fashion. Now, when you've got something as tedious and as detailed as this, there's no such thing as truly automated. There's always an element of hand-holding that has to happen. But we're working on a program, a computer program, where you can just stick your data in and it will spit you out the, what it will actually give you is the, it will give you the true value of this. So you can see here how this has been cut off. It's been sort of saturated. So what it will do is it will work out what the true value of this should be. And it's usually, you know, 15 to 20 times bigger than whatever this maximum value is, which means that you can go back to your images, like this image right here, and work out what the actual pixel value is and start to see detail. The same way as you can see all of this fine detail here, we want to be able to put that fine detail back into the middle of these images. And then also as a byproduct of that, we're trying to create a way to do this just dispersion spectroscopy at the end of the day as well. It's sort of an afterthought right now.
Okay.
Yes, the idea is that to go back through the archive, we have to be really careful about the events that we choose, because if you have a really messy event with loads and loads of saturation, then all of the diffraction patterns get all blurry and cross over each other, and it's really difficult to pull out the signal, which is why that other event was nice, because it went off the limb of the sun, it went off the edge of the sun, so you didn't have any background contamination, which is something they have to be careful about. But the hope would be that eventually we'd be able to reconstruct a significant amount of the flares that we've seen.
That's cool.
I love Nancy's comment about how it's such a great connection for students to see the real science. And I always call it I think of it as a Post-it note moment. Like, that's not what you meant to discover, but here's what you found when you were doing something else, and you get Post-it notes. So it's really great.
This is pretty neat science, because like I was saying, all of the other instruments that are designed to do this kind of work have either really small fields of view, and if you're only looking at a teeny tiny region of the sun, then at any given moment you could be pointing at over here, and a solar flare could go off down there, and there's not enough response in these instruments to say, oh, look, go down there, look over there, and then you miss data. Actually, when I started as a PhD student, part of my impetus for doing this project was I was waiting for an instrument, a Japanese instrument, for 4 years to give me solar flare data, and they missed every single flare. It was like a series of unfortunate events. Or they don't have high enough cadence. You can't take enough data regularly to be able to make it worth your while.
Nice. That is so cool.
So, anyway, I just thought I would really, I just wanted to share that because I think it's cool. I figured why not.
Well, and that's real life engineering too, right? Trying to figure out how to develop the instrument to solve the problem that we need.
Yeah. When I started doing this project, actually, we went to talk to some folks down at the Lawrence Berkeley Labs about the idea of building a telescope where every pixel gives you this data, and we got into the crazy world of looking at using quantum dots as your detector systems, and then we realized that it was way beyond where we were about 10 years ahead of where technology was. So we'll revisit in 10 years.
That is so super. Thank you for sharing that, Claire. Well, I am so sorry that I've missed so much of this. It sounds like it has been a very spectra-filled time together, and it's so neat to see so many faces here. I'm so glad to see that everybody was able to come.
Yeah, this was an especially rich meeting. I really enjoyed this. One thing that I really loved was hearing from each one of you about how you use spectroscopy in your classroom, including Claire. So we heard about how to use it in an informal setting, in an elementary school setting, middle school setting, high school setting, and a research setting. It was really, really cool. Thank you so much.
I was excited tonight as we were trying to get off the plane, and I had the activity pulled up on my computer while we're waiting, and my daughter looked at it, she goes, "You can do that with a cereal box?" I said, "Sure," and she said, "Oh, we've done something like that. I could lead that activity." So I was like, oh, I got all excited for a second. I had no idea my daughter had used those.
I wonder if you could do some engineering experiments with that to try to solve different problems, kind of expanding on what Claire was talking about tonight, how she solved a problem using some engineering. I don't know how to phrase it, but
I was actually curious if we could modify the design so that it would work through the laptop, since the angle of the DVD in the box was optimized for looking through, but maybe not for the laptop camera angle. So
that was my hope for challenge. I'm sorry, I apologize, Dawn, for if you've already said that, but part of what I'd hope people could do was exactly that, Lindsay, is figure out how to take some images of what you can see with your spectroscope, especially some of you who have light tubes. If you can have or if you live around where there's sodium lights or any of those fun things, that if you can post some of your image data on the Wigio about what you get using your box spectrometer, or spectroscope, that would be fantastic.
I was going to say, what does Nancy's sunset look like? It looks like she's got sunlight streaming in her window. You must have your cell phone right there. No? Can't hear you.
I'm sorry, I have the window. I have all the windows open in my house. It's like 77 degrees here, beautiful allergy season. So I've got kids outside. They're playing ball in the street. They're playing baseball. So they're periodically I'll kind of see them kind of do something going by. So that's what I've got going on over here.
No, but I was just saying you could point the spectroscope you made and try and take a picture with your cell phone camera.
I thought you knew what was happening right now, and I'm thinking,
no.
Outside.
No, I meant you could take a picture right now of what your sunlight looks like through your.
I could.
And share it with us.
Through my box. Okay, hold on. Let me see if I can figure this out.
While Nancy's doing that, if I can share my screen real quick, I just wanted to remind Jennifer Taylor wasn't able to make it with us tonight, but I wanted to remind you that in her lovely SDO project suite, she does have a whole activity where you build a very similar spectrometer, and some great activities in using the data from using the spectroscopes. I'm sorry, I use those phrases interchangeably. But in that SDO curriculum suite, and this is activity, I believe it is 2C. Yeah, 2C. So the module 2A and 2B build on what spectra is, and then the students build the spectroscope and use it in this activity. So those are all on Wavelength now, as well as I believe she posted it to the Widgeo if you that's something that you're all interested in taking it a step further with. And I know Wendy also has a lovely list on Wavelength of all sorts of spectra activity that she's put together. Perhaps she will download it and post it to the Widgeo for us, and we can all, she has it all arranged really. I found it on accident. I was looking at something else, and I was like, wait, Wendy's already got a list. Click. It was great.
Okay, there we go. Oh, jeez.
Also, some of you, I know you were talking back and forth, and I'm so sorry I've missed so much of this this meeting, but some of you do have diffraction grading, and I think it would be interesting to do both kinds. I know there's on Wavelength, there's another activity where you use diffraction grading to make a spectroscope, and I'd be interested in seeing what kind of different images you get from and compare the two. I know some of you have used some of them, but I would be interested to see what the differences in the feedback are.
Oops. Nancy, is that where you put your eye? You need to put the camera where you put your eye.
Oh, yeah.
And here, folks, is why we practice our science things before we demonstrate them for our students.
Oh, my God. Trying to figure out, why is this not working? What's wrong with me? Well, a lot. Yeah.
It's late. You had a long day already.
Well, we've had state testing today, so yeah, I'm brain dead. I've already had some wine. Okay. All right, hold on a second.
You could just post the picture later. I thought it would be.
I can, yeah, I get it. I get it. It's just, it's way cool. Okay, wait a minute. I think, yeah. What's really sad was when I got this new iPhone thing, I told, whatever it is, I asked one of my students if she would do me a really big favor by showing me how to use it. And I told her I'd give her a free 100, you know, for the class period, thinking it would take her a long time to do this. No, within 5 seconds, she showed me how to turn it on, turn it off, and do something with alerts. Yeah, it was an easy 100 for her. Still took me a while. Okay, yeah, I will definitely, all right, let me see. See if I can figure out. So do you want to, well, okay, well, anyway, oh, where did that come from? That's not mine.
Lynn beat you to the punch.
I did, no, I didn't do that, did I?
No, that's Lynn's sharing that image.
God, I thought oh my.
No, that's mine.
Okay, whoo! I thought that I just totally did something that I didn't know that I did. Thank you. Because mine looks like that. Okay, so, wait. See? See, so, yeah, it's not like going on there. Okay, I'll be quiet now. Oh my God.
That is so awesome. This is why we have this group, so we can experience these things together.
Thank you for being patient with me. But yeah, it is. It's very cool. It is the coolest thing. So, but yes, mine look like hers.
How many people are going to have their students build CD spectrometers?
Oh, yeah. Oh, yeah, absolutely, absolutely. And then I'll have them teach me how to actually really take a picture of it the correct way and then put it on our Google site. That would be fantabulous.
Extra credit. And then if they get it right, they get extra credit.
Yeah, teach Miss Stout how to do it. Yeah. Oh my God. Can't believe I did that. Yeah, that was very cool. Thank you very much for the whole thing with it. And Claire, it's always so wonderful to be able to hear what you have going on. Just what I really enjoy about listening to everything that you do is that the more that I learn, the more I realize I can learn so much more. And so it's through people like you that make me feel good about learning more about science and sharing that with my students, because who knows, one day one of my kids might be like you and be there and giving us the information that you're giving us now, or better information, more information, whatever they come up with. And I love it, and thank you so much.
Shucks, Nancy, you're making me blush.
Nah.
I'm always happy to share. It's always such a pleasure. So I'm glad it's a win-win all around. Now all I have to do is get my act together. I'm presenting this work at a conference in Indianapolis next week, and
yay!
I'm not ready at all.
Well, I'll have a margarita for you.
There you go. Thank you.
Yeah. And if you come down here, I'll take you to all the really great margarita places.
Good stuff.
Yeah.
Right. Anything else from me?
Okay, let's see.
So one of the things that we were trying to achieve today was, I think we felt like last month it was a great presentation from Phil Chamberlain, but it may have been kind of high level to some degree. And what we were trying to do was kind of take that back to the classroom level and try and make the connections between the far-fetched spectroscopy scientists stuff doing their thing and how you actually apply this in your classroom. And I guess one of the questions is, do you think that A, was that worthwhile, and B, did you think that we achieved it this week? Is there something else that we could have done to help connect last month's presentation a bit better?
Well, I, for one, think that we achieved a lot as far as bringing this very cool Lucera box, thank you very much, bringing this in and really tying a lot of things together. As I think Vic may have said, this is something that the kids can take, they can go out. I know that I would appreciate them taking this and going out and looking at a lot of things, getting more excited about it. I mean, look what I can do, look what I can see, and then showing their parents, and then somebody else showing someone else. In my area down here, I just got a huge inflow of children from the Colorado area, and their parents work for Sierra Nevada Engineering, which is the spaceport. So they have a whole interesting background that we're going to need to start addressing at my school. And so this is something that they are certainly going to be taking and running with. I can definitely see that now, and I'm thinking of 3 students in particular.
Vic, were you saying something earlier? I saw your mouth moving, but maybe you were admonishing students. I don't know, or directing them to.
Why do you think it's always negative?
I wanted to give you the benefit of the doubt. I thought it was.
A student came in and had a pretty good wine, and so I did some condescending. Yeah, you can turn your assignment in. It's still open. Go do it. So I was talking to a student, but I wasn't being this time.
I thought everything was great. I've got a lot of ideas.
Well, I sure hope that I sure hope you share them, Wendy, as you unfold them and work with them, and the more that we can help each other out that way, and it would be really lovely to we're hoping that if this works for you, we'd like to do a lot more of this in the future as people, making that connection back to your classroom for you, so that you looking at the response in the chat of everybody who has done work like this or has done work like this, and all of the different diverse ways that you've used it, and the ideas that have come off of from viewing it. So we're hoping that will be so we can ask you to all help us do as we look at more subjects.
I can put more on the Widgeo with my list, and the order that I do things in and how it all melds together. I can put that on there.
That would be fantastic, Wendy.
I still like to think that I'm still stealing stuff because, for example, after what Claire went, you know, I've been doing this physics lab with lasers since the lasers were invented because you knew the exact frequency of them. And we were using the frequency and how to determine the frequency and the wavelength from a distance setup in a class that you can do in a classroom. And actually, surprisingly, you get fairly close data. I'm just kind of glad to see that the stuff I'm teaching, it gives me a little more energy. It's actually used by somebody. It's just not spitting in the wind. And I use a fair amount of spectroscopy through my classes, but it's just kind of fun. I think the real important thing is, you know, these little cheap ones, they're $30. They're not cheap, but you can get building cardboard ones, and like you say, they can take them home. Now, most of them will end up in the trash, but there's a couple of them that may be used, and that's what you look for. Not everybody can be an engineer, but you get one per school per year, and we can meet our demand.
That laser thing, Vic, I've never heard of that. So he put that on the Widgeo for everybody, because I mean, I could use that. It's just these kind of things where we can share each other's ideas and get stuff from each other. That's what, you know, we help each other out, I guess. That's awesome.
That's
Make sure
that's
you put
why
it on there, Nicole.
I like I say, I steal little ideas from everybody.
Yeah, I know, me too. That's what we do.
Community learning, is that what we'll call it?
/ fun.
Like a nationwide study group.
Well, we're about out of time, everybody. Unfortunately, tonight went by so fast. And thank you so much. This was all because of you guys, all of your sharing. And we will be, like Andy said, we will be reaching out to you. And please reach out to us if you have an idea that you can share with the group in the upcoming meetings. I believe our next meeting is May 19th. And it seems like a long time away, but it'll actually fly by again. So I'm looking forward to seeing all of you guys. I have to jump off here soon, but you're welcome to continue to talk. I don't want to interrupt the great conversations that are still going on, but if not, I will. I'll see you next month. Thank you so much, everybody. Bye-bye.
Thank you, Dawn.